Hi, welcome back. Today we're going to talk about the trig functions and how that will be applied to vector addition. With trig we can use triangular properties and apply that math to the graphical representation of vectors. And so we can find the component vectors and the resultant vectors mathematically instead of trying to graph everything and do tip to tail and start to finish to find the resultant. Okay, if we take a typical right triangle, the hypotenuse is going to be opposite of the 90 degree, it's an angle, and then adjacent and opposite can switch depending on which angle we're concerned with. The opposite leg is always going to be opposite of the angle of concern, and then adjacent leg will always be part of that angle. And so if I switch this now becomes my opposite leg, and this becomes my adjacent leg. Notice the hypotenuse doesn't change because it's always opposite of the right triangle. Now, understanding this, there's a really important triangle principle. All angles will add up to 180 degrees. And so we had a 90 degree angle, that's the right triangle, and then let's say that theta was 32 degrees. What I did here was I plugged in all of my angles. This was theta, this was theta 1. These will all add up to 180 degrees, so if you just subtract them from 180, you'll end up with 58. And so I can find out the other angle if I can use some trig to find that first angle. SOHCAHTOA. SOHCAHTOA stands for the sine of theta is equal to opposite over hypotenuse, cosine of theta be adjacent over hypotenuse, and the tangent of theta will be equal to the opposite over adjacent. So these rules will help us solve for missing legs of a triangle given a known angle. We can use this to take the anti-sine, anti-cosine, anti-tangent to solve for an angle. So if I did know the opposite leg and the hypotenuse, I could take the anti-sine of the opposite over hypotenuse and solve for theta. If you are unfamiliar with these trig properties or need a refresher, M8 in the back of the book will review all of this information that you may or may not have been taught or forgot, or maybe you just need a refresher. There's another way to look at these triangles. If I don't really care about the angles and I just have an understanding that this is a right triangle and I have legs of A and B and I want to find the leg of C, maybe these are vectors and I need to find the C vector, I can use Pythagorean's theorem. Now in the book these will often be called the resultant vector A has a y component and an x component. And so it will be a sub x plus a sub y. And we're going to continue using this form as we move forward, just so that we stay in rhythm with the book and what AP is expecting. Okay, vector form. Vector form, there's two main vector forms that we'll use. Okay, so this standard vector here, remember we always measure the angle to the nearest horizon, and it has a magnitude of this length, and so we have the angle showing direction and then the length showing magnitude. In polar form, I would write this vector in terms of a comma theta and then the quadrant that I was in. Now if you need a refresher, the quadrants of a graph, this would be the x and the y lines. You have quadrant 1, 2, 3, 4. And so this vector we could say is 5 meters 30 degrees in quadrant 1, just as an example. Now this is typically how we talk about vectors. I would say, well, it's 5 miles this way, 30 degrees off from north, right? Or 30 degrees south of east. and that would be descriptive enough for you to understand what that vector was. But mathematically, this is very difficult to handle, and so if we're going to do any kind of math, we're going to want it to be in what's called rectangular form. Rectangular form takes this x, y coordinate system. And so on your grid, we understand that this is going to be positive, positive. This is going to be negative, positive, negative, negative, and positive, negative. So if my values of x are positive, I know I'm going to be over here on the right hand side. If my y values are positive, I know I'm going to be up here. And so using the x, y, positive, negative system, I can tell where the direction is for my rectangular form. And so an example, you might be negative 1, 4, and you would very obviously see that that's negative 1 in the x, so it's going to be over here, positive 4, so this vector is going to be somewhere in this area. Now, when we are dealing with this standard vector form, whether you're in polar or rectangular form, there's some math that we can use to apply to this. So we're going to take some of those trig properties and put a vector spin on them. Now, traditionally we would say that this is theta, and that's the hypotenuse, and that's adjacent. Now, because that's adjacent, anything adjacent over hypotenuse is going to be the cosine, Ka, K-A-H. So cosine of theta is equal to adjacent over hypotenuse. In this, how it's written here, my hypotenuse is actually A, and my x component here, my adjacent value, is actually A sub x. And so I can rewrite this in terms of the values that I'm using in this vector would be A cosine theta is equal to AX. And so it's the magnitude of the vector times the angle is equal to the x piece. So this is basically, it's not a percentage, but you can almost think of it as a percentage. This is the percentage of the x which the A is operating in, because some of vector A is in the x dimension and some of vector A is in the y dimension. Now, it's not quite the percentage, but you could think of it that way. We can do the same thing with sine. And so this is the opposite position, hypotenuse, and so if I want to find this value, I would use the sine function. So the sine of theta is equal to opposite over hypotenuse, and then in terms of what I have up here, that's going to be A sub y over A, and then I can solve A sine theta is equal to A sub y. So again, this is the magnitude of vector A, and then you could almost think of this as the percentage in the y dimension, and so the percentage of A in the y dimension is going to be A sub y. That's the component of y, and then this is the component of x. You should certainly have these in your formula toolbox, maybe a box off the side of your notes. And then we'll just rewrite it. You also have I don't know where to stick it. A is equal to the square root of A sub x squared plus A sub y squared. And so that's another way. If I knew my components and I wanted to find the vector value itself, this wouldn't help me with the angle, but this would help me with the magnitude. If I wanted to use the angle, find the angle, I would have to take the anti-cosine or the anti-sine. Well, that's it for vectors and trig. Think of those formulas as a toolbox that we can apply to various situations, and as we move along in this course, you're just going to have more and more options to apply to the situations, and the math is not going to become the hard part. The hard part is going to figure out which physics principles can I apply to this situation. And so try and keep that in the back of your mind, and we will do more practice in class to help you figure that out. Alright, thank you.